Okay, now let us just revise that AC part one more time. See, AC means alternating current. So it means the current or voltage is varying with respect to time. Time is shown in the x-axis. So you can have either V or I on the y-axis, and it varies with time. Now how much time it is taken to repeat the cycle that you call as a time period. So when you see an AC equation, it will be like this: V is equal to V0 sine omega t, where V is the instantaneous voltage, V0 is the peak value, sine shows that it is an harmonic function, means periodically varying function, omega means its angular velocity, and t is the instantaneous time. So what do we mean by peak value? Peak value is this much value, the maximum value it can have. What is instantaneous value? Instantaneous value means any value of the voltage at any instant of time. At this will be t1. So at this instant, this is the instantaneous value. Now omega can also be written as omega is equal to 2 pi times frequency. So normally a question will be asked related to this, what will be the frequency? I will just come through it. So omega can also be written as 2 pi f. Please note down. Now so instantaneous everything. Similarly you can write for I also. I is equal to I0 sine omega t. Same logic applies. I is instantaneous current, I0 is the peak value, sine is a periodic function, omega is the angular velocity, t is the instantaneous time. Now uh, since you can't have the average value over a full cycle, because when we take the average value, if this is a cycle, means this is, you will have a plus 5 here, you will be having minus 5 here. So if you take the average, you will get it as 0. So average value of AC is only taken for half cycle. So half cycle means only one part they will take, and it is given by the equation I average is equal to 0.637 times of I0. So I average value is equal to 0.63 times the maximum value. Note down this equation. Similarly, RMS value, another term to be used is RMS value. So I RMS is equal, RMS means root mean square value. Okay, so they will divide this into small intervals, find I for each, then they will square it, then they will take the average, then they will take the root. So that is how the root mean square value comes in. So you need not look into it, you only want to have that equation. It is 0.70 times I0. So I RMS is equal to 0.707 times I0. Sometimes it will be written like this: I RMS is equal to I0 by root 2. Similarly, V RMS is equal to V0 by root 2. Another thing to be noted down is an instrument always measures the RMS value. So if they will give a voltmeter measures the voltage equal to this much, so that is RMS value which is shown. In some numericals they will say. So this is about I average and IRMS. Next, when you apply this AC, so you have three type of components. Either you will be having a resistor, or you will be having an inductor which is a coil, or you will be having a capacitor. So when you apply the AC to a resistor, inductor or capacitor, the voltage and current, let this be the current, sometimes will be going together, sometimes someone will be leading, sometimes someone will be lagging. So when you check that, you can see that in a resistor shown by R, inductor by L, and capacitor by C. So in a resistor, voltage applied, AC voltage applied, and current, AC current, both goes in phase. So you can write V is equal to V0 sine omega t, and here also I is equal to I0 sine omega t. So both are in phase, there is no phase difference. Sometimes the equation will be like this: V is equal to V0 sine omega t plus phi. This phi indicates the phase difference. So in this case, both are having the same phase. Okay. Now if you draw the phasor diagram, you can see that both are moving together. So if this is voltage and current will be on the same line. Now if you go for inductor, the current lags behind the voltage, applied voltage. So V is the applied voltage, V0 sine omega t. I will be lagging because of the back EMF. Okay, because of back EMF. So I will equation will be equal to I0 sine omega t minus pi by 2. So it lags behind the voltage by an angle of 90 degree. So if you plot the phasor diagram, so it will be something like this. You can check in your textbook. If the voltage is leading, then current will be lagging by an angle of 90 degree. So voltage will be up and current will be down by an angle of 90 degree. Now in case of capacitor, V is equal to V0 sine omega t is what you apply. In that case, the current leads in the voltage by 90 degree. So it will be I0 sine omega t plus pi by 2. So the phasor diagram will be something like this. In place of V, you will have I. In place of I, you will be having V. So it leads. So always the phasor diagram is drawn anti-clockwise direction. Okay. Now the resistance offered or the hindrance offered by the inductor is called inductive reactance, because they can't use the same word again and again. Resistance is already used here, so they will say it has inductive reactance denoted by the letter XL. Similarly, XL can be written as L omega. What do you mean by L? L is self-inductance denoted by, the unit is Henry. So in some questions you can see Henry, if it comes, it means L. Okay, H. Now similarly, the hindrance offered to the AC by capacitor is given by capacitive reactance denoted by the letter Xc. So Xc is actually 1 by C omega. What is C? C is capacitance. Now omega, I think it is clear. Omega is angular velocity. So this is about AC through a resistor, AC through an inductor, AC through a capacitor. In an resistor, both are in phase. In an inductor, current lags behind the voltage by an angle pi by 2. In a capacitor, it leads the voltage by an angle pi by 2. Resistance offered or the hindrance offered by the inductor is called inductive reactance, shown by the letter XL. It is equal to L times omega. Similarly, hindrance offered by capacitor is called capacitive reactance, given by 1 by C omega. Now normally a question will be a graph type question will be there. How do the inductive reactance and capacitive reactance varies with frequency? Now if you check the equation, you can see XL is equal to L omega. Omega can be written as 2 pi f times L. So this you can write like this. So XL is proportional to L. So if you draw it's proportional to frequency. So if you draw the frequency on y-axis, XL on the frequency on x-axis and XL on the y-axis, it is proportional, means it will be a straight line. So they will give 4 graphs and ask you which is for the inductive reactance. Now if you check for capacitive reactance, it will be X is equal to 1 by C omega. So 1 by C times 2 pi f. So Xc is inversely proportional to f. So the graph will be like this. So means frequency increases. If frequency increases, Xc will decrease. So if it is Xc here, the graph will be like this. Hope you understood this. Next, impedance. So see, impedance is shown by the letter Z, because there are other component, resistor is there, inductor is there, R is there, XL is there, XC is there. The whole effect is shown by this letter impedance. Okay, impedance means the combined effect of impedance offered by these three people. So if you have an LCR circuit, uh, now one circuit is there, I mean I will come to it later. So there is an LCR circuit in series, means L is inductor, C means capacitor, resistor in series, so LCR circuit. So in this LCR circuit, normally we assume the inductor is having a more influence than the capacitor. So this, they will write R here, then XL will be here. Better I will write in terms of the voltage. So VR, voltage across the resistor, voltage across the inductor, this is voltage across the capacitor. So if I assume the inductive nature is more, then I can write it like this, because V is equal to IR. I is common for all, so I can write R here, then XC here, then XL here. Then if I take this to the uh, other quadrant, then it will, this difference will be equal to XL minus XC. And if you consider this as XL minus XC, this XL minus XC, then this will be the impedance of the circuit. That is how you get the equation Z is equal to root of R squared plus XL minus XC the whole square. So this indicates, or this Z means the impedance offered by the whole circuit. Okay, now similarly you can write the equation for voltage also. So voltage equation also can be written like this: V is equal to net V is equal to V across the resistor the whole squared plus V across the inductor whole squared minus V across capacitor the whole square, like this. So you can write V is equal to root of I times R squared plus I times XL minus I times XC the whole square. So you will take I out, so this V can also be written as uh, I times Z. So you will take the I out, root out means only I will be remaining. So that is how you get the equation Z is equal to root of R squared plus XL minus XC the whole square. So normally one problem will be from this part. They will ask you uh, when will be the impedance of the LCR circuit will be minimum. See, for this to be minimum, you can't change the R. It is a component, but you can adjust the values of XL and XC by changing the frequency of uh, the AC, because XL is equal to L into 2 pi f. Similarly, XC is equal to 1 by C into 2 pi f. So it depends upon frequency. You can change the frequency so that both becomes equal. So this term will become 0. So Z will be equal to R when XL becomes equal to XC. So that is, the circuit will be providing the minimum impedance when XL becomes equal to XC. And this situation or this phenomenon is what you mean by the resonance. So at resonance, the LCR circuit's inductive reactance and capacitive reactance will be equal. The circuit will provide the minimum hindrance to the AC. It means maximum current will be flowing. So you have, because the questions will be related to this. So during resonance, XL is equal to XC, that is during resonance. Then that frequency is equal to 1 by 2 pi root of LC, the frequency at which this is happening. Then Z will be its minimum value given by the resistance of the circuit. Then current flowing will be maximum in that case. Next, when you plot a graph between the current flowing through the circuit and the frequency, that is omega value, if you write down the angular velocity, because it is equal to 2 pi times f, so this 2 pi being constant, I can consider it to be equal to the frequency. So if you draw a graph between omega and the current, then you normally get a graph like this, because at lower values also the current will be less, and higher value also the current will be less. So the peak at which this happens is what I told you. The current will be maximum at a particular frequency. You call it as the angular, resonant frequency. So you will have normally have a graph. So this will be written as omega 0. Actually, it means f0, resonant frequency. Since f into 2 pi is omega, so they will sometimes write it as omega 0 also. And you will have half power frequency. So I will tell you what it is. So the graph falls down in both sides. So where the with this current you will be having a power, and I am checking for those areas where the power becomes half of what I have got here, and that particular frequency where it happens on this side and on that side, I will write it as omega 1 and omega 2. For this particular current I'll be getting some power value. Power is equal to V into I. Okay, and I will check for the uh, that particular frequency where the power becomes half of it. Don't look into the graph. You may think I should draw at the middle. It's not like that. Power, I'm not saying about the current, I'm saying about the power. So the power should become half of what I have getting here. So that particular frequency where this happens on both sides is what I mean by omega 1 and omega 2. The difference between these is what I mean by bandwidth. So difference between the frequencies, so bandwidth is the difference between the frequencies where the power becomes half of what I receive at resonance. Now this can W2 minus W1 can be you when you derive, you will get a relation like this, will be equal to R by L. So bandwidth is equal to resistance of the circuit by inductance of the circuit. So it means bandwidth depends upon the resistance. Okay, if the value of R is small, the bandwidth is small. If the value of R is more, the bandwidth will be more. Now what is the speciality of bandwidth is, see, if the bandwidth is less, mean uh, the selectivity or the curve will be much more sharper, so curve will be falling like this. So you are getting a graph which is much more sharper. So if bandwidth is less, the curve is sharper. So bandwidth is the difference in frequencies at which the net power becomes half of what you are receiving, or what is at the resonant frequency. Then bandwidth is equal to R by L, and if R is less, bandwidth will be less. So bandwidth is less means the curve is becoming much and more sharper. Okay. Now there is another term which you call as the quality factor. Quality factor is denoted by Q. How useful the given circuit is to select a particular frequency, that is decided by the quality factor. Okay, so quality factor is given by omega 0, that is the resonant frequency, by bandwidth. So resonant frequency divided by bandwidth gives you the quality factor. So its equation will become like this: omega 0 divided by R by L. So omega 0 times L by R. So Q is equal to omega 0 L by R. So earlier I wrote Omega 2 minus omega 1 is called the bandwidth. It is the difference of the frequencies where the net power becomes half. It was equal to R by L, and quality factor is equal to resonant frequency divided by the bandwidth, which will be equal to omega 0 L by R. So smaller value of R means bandwidth will be less. Bandwidth less means sharper will be the curve. Sharper the curve means more selective the circuit is, that is the quality factor will be more. So you can write like this: R is less means bandwidth is less. Bandwidth less means sharper the curve. Sharper the curve means more is the quality factor, or more selective the circuit is.